Welcome to the Beyond Worst Case Complexity panel. So we're going to be talking about, criticizing our favorite way of analyzing algorithms. And we have a very, very distinguished panel with us. There's Piotr Berman, Avrim Blum.
Keep going.
Am I?
Indyk.
We have a very tired moderator tonight. Piotr Indyk, Avrim Blum, Shang-Hua Teng, Santosh Vempala, and Ravi Kannan. Got the rest of the names right? No, but that one's difficult, so I get a pass on it. And so what I'm going to do is have the panelists give a short presentation of their views on the subject. Then I'm going to ask them some leading questions, try to get some discussion going, and then we'll also take questions at any time from the audience. Okay, so we'll start with Ravi. So have your presentation. Oh, do you want to? You could also just.
Oh, you would do the page count?
Yeah.
Okay, yeah,
Just tell me. Okay.
But it's all full the time.
Oops, that did not work so well.
So full page view. You want? Yes.
There's this.
There's a full page.
No, that did not. What?
Yeah, it's not my issue. Somebody's coming.
How about this one here?
Okay, that's it. Yeah.
Okay, and you're here now, so.
Yeah. So I'm going to start with a famous quote, which goes, "Nothing focuses the mind like," and usually the likes are death and taxes, but there are other versions of it. I would like to add to that worst case complexity. Because worst case complexity, it's not the World Cup cricket, it's WCC, I abbreviate worst case complexity. Since the 70s, worst case complexity has focused the TCS mind rather well and sharply, resulting in some great intellectual advances. So I want to praise WCC on this slide.
Good. Hold it just closer to you.
Okay, is that better?
Yeah.
Yeah, so we start again.
No, it's just going. It's just keeping.
So it's resulted in some great intellectual advances in both algorithmic ideas and hardness proofs, both sides. And NP hardness, for instance, is an example. One more. Okay. One common refrain that you hear is not practical, the time bounds are too high. Well, the theory aesthetic always is a clean abstract model which doesn't bring out all the complications of reality, but serves as a foundation for scientific advances. In that, WCC has been a great success for the last 50 years. Now, the other complaints, one I won't deal with. One complaint is, this complaint is WCC outweighs simplicity and generality of the algorithm. I won't deal with that. Instead, I'll deal with something that's unusual, perhaps.
Ignore it for now.
This is a very eventful talk.
Yeah. Okay, actually, now I'm getting nervous. Why don't you come back over behind the podium?
Yeah. So worst case data can give us pessimistic time estimates. This is obvious and heard a lot. And one attempt to tackle that, the first attempt is average case analysis. But a less well-known or less heard about complaint is, in fact, worse. It can give you wrong conclusions. So, for example, if you have insufficient data for scientific or social phenomena, you run an algorithm, what you get out of it is not going to make sense, right? Now, what's the general complaint? Here's a general complaint I want to focus on. WCC has in fact focused our mind on something, but it has focused it away from understanding data. This is overstated, pardon, but this is all I can put into one bullet. Highly qualified, but I'm saying we're ignoring data. Highly qualified again. So statistics and machine learning do worry about what data looks like. They build models of data. In the main, the models have a feature that data points are independent of each other. There's no adversary coordinating the whole data set. Okay? And they're picked from some general distribution, not necessarily uniform. So is there a happy marriage for the future? You take these data models and prove that there are certain properties that hold under them, and then in the worst case data with those properties, we prove time bounds. The answer is, I think, yes, but instead of describing generalities, I'm going to give you one snippet, and this is my last slide. So here's a possible talk in the next 20th anniversary of Simons. And the main theorem of the talk is that this particular self-driving program is 5.9 safe, index of 5.9 safety. So that's that. Okay. Now, it's just not one single theorem. I want to point to a lot of theory that underpins that. Theory would have, in the process, accomplished the following before going to this theorem. First, would have formulated a stochastic model of data. Second, would have proved possibly deterministic properties that hold with high probability under the model, given enough data. This is data sufficiency, which plays a big role nowadays. And the third part would have proved that for any even worst case data, but satisfying the properties, the program works. So I just want to summarize in 2 lines what the general picture is. Well, before that, won't you feel safer reading this proof before you drive the self-driving car? I guess that we, as theoreticians, we would. Yeah. Now, properties are possibly deterministic. As I said, they are really explanation of features in deep network or whatever you're using, which at the moment is sorely lacking. We don't have explanations of what DNNs do, and theory could actually answer that question. The second is data sufficiency, which we know under the name sample complexity. And we have our own beautiful theory for supervised learning, a la PAC learning. We don't have a theory for unsupervised learning, and that is one of the agenda items that underlies such a theorem. Okay, yeah, that's all I have to say. Thank you.
Thank you. No, you keep that one. Okay. Yeah.
Your PowerPoint skills are amazing.
Well, yes, but amazing in what direction? It's already here. Is this yours?
Yeah, this display thing. This.
Okay.
Okay, great. Thank you. My view is, how should I say, much less exciting. No self-driving cars, no whales, no mermaids. But it's 3 slides, 3 problems that I think are still going to drive a lot of work in the next decade. The first is planted clique. Actually, we can first talk about clique in a random graph. So worst case is we sort of understand the answer. But how about in a random graph? We know there's a 2 log n. Greedy is log n. We don't know how to find 1.1. And the first director of the Simons Institute asked this question. It's still open. The current best we know how to do is log n plus root log n. How many of you know how to do log n plus root log n? Okay, let me tell you. It's very easy. So you have a little nugget. So log n is just you take a vertex connected to it, vertex connected to both of them. That's it. That's builds log n. Okay. To get log n plus root log n, you do the following. You do this greedy thing, but you stop at 1 minus epsilon log n. Okay. Now, when you have 1 minus epsilon log n to the epsilon of the remaining vertices will still be connected to all of these guys. Not between each other, but they'll be still connected to all of each because it's probability half. Okay, so you have n to the epsilon connected to 1 minus epsilon log n. And now in n to the epsilon, you know there is a 2 epsilon log n clique, because that's still a random graph you haven't looked at. How do you find that? Brute force search. Because that's n to the 2 epsilon squared log n time, set epsilon to 1 over root log n, and you've got root log n. Okay. Can you do better than this? I don't know, but it would be great. Okay, planted clique. So this is, if you make k much bigger than log n, so Jerome introduced this to try to make progress. Root n is where we are stuck for all kinds of algorithm classes, low degree, SQ, so the right versions of SOS for this, at least to refute the existence of this clique. But it won't surprise me if tomorrow one of you or Feige comes up with a root n over log n. Nothing stopping it really. Okay. Random planted KSAT, KCSP, sorry, very much in the same vein. But this one is very rich, right? Because we have these phase transitions, that statistical physicists have observed, and now theoretical computer scientists are formalizing. And it's terrific. We understand certain things about where these thresholds come up, but they also exhibit these computational gaps, statistical computational gaps. So in particular, we know that with n log n clauses, it becomes unsatisfiable with high probability. But to prove this or to refute it, you need n to the r over 2 clauses, where r is basically the how many way independent your clause distribution is. If it's r minus 1 way independent, but not r independent, that's r. Okay. So in particular, there's a hypothesis by Feige which says that just 3 sat maybe needs n to the 1.5 clauses, even though you know that after n it's already unsatisfiable. So, fantastic problem, right? And very different from the usual. And this is my last slide. Random games. So if your payoff matrices are with independent entries from at least we know for Gaussian and uniform, but probably holds for much more general distributions, then you can find a Nash equilibrium, a real Nash equilibrium in polynomial time. So that suggests, how about smooth? That would have been great, right? How about if instead of random games, I take an arbitrary payoff matrix, I perturb it in the usual smooth sense, and then now can you get something? There turns out that it would have been nice, but it actually implies an epsilon Nash equilibrium, and apparently now this is a hard problem unless you think that PPAD can be solved faster than exponential time. So even approximate smooth is hard. So what's a good model in between, or what can we do for games beyond random games? That's it.
Thank you.
So since Russell gave us a very general instruction, and I and Avrim are the two camps without doing slides, and so you can see the case are different. And so instead of giving a concrete conjecture as the early two, I would like to just offer a little bit of perspective where somehow lead my own thinking over the years toward the notion of beyond worst case analysis. And because we are living a changing time for computer science, right? Everything is rising. There's a lot of new domains that we enter. And usually those times somehow give us a new language and new measurements. And for myself, basically, as a theoreticians who clearly take all my classes in worst case analysis and polynomial time computation. And then I suddenly transferred from USC to CMU as a student. And at that time, CMU, however strong they are, has only a few theory students. And most of my classmates were not from theory. And because CMU randomized the students, I suddenly being exposed to things that was not teaching theory class, right? So the first thing somehow impacted me, I think could be an example, just impact every generation with their own instance, is in CMU, one of this development is a so-called BDD, binary decision diagram, which is a critical tools for circuit design. And my office mate was studied under Randy Bryan. So every day he's telling me BDD. And very quickly, I realized the whole thing is NP complete. I just shut down. Mm-hmm. But he's continued to look for this particular ordering of the Boolean order, and then to make this diagram in finite state automata very short. And then they have consequence. If that is small, then some other thing, great thing happened. And so as a theoretician for a while, I was very fascinated by the fact that they find this natural way to attack obviously an NP-hard problem, right? And so clearly BDD has been a theory, has been developing. And in fact, I was surprised years later to read this beautiful blog from Lipton. He wrote a long essays about the BDD. And so I said, no wonder that also deeply impacted myself as a student at CMU. And so then after I graduated, I went to NASA. So in that days, web is a supercomputing. You know, everyone tried to predict earthquake, fluid dynamic model, and so on. And I went to NASA, and this man, his name is Horst Simon. I think he's near Berkeley now, Lawrence Berkeley Lab. And so he was a student from Berkeley, from numerical analysis. And then he specialized in writing Lanczos code and solving eigenvalues. So then suddenly 90s happened, everyone is running the parallel machines, and people want to do graph partitioning. And when we were looking around, everything's going to be complete. And so I went to NASA, and the first thing Horst Simon said to me, he said, Shang-Hua, you have to read our experiments. It's so sharply find a great partition everywhere. And there must be a theory in it. And at that time, I was thinking, I said, you know, how can you convert just this observation to a theory? And at the beginning, I haven't overly analyzed, but somehow it deeply registered to me that this very popular code, which I find in NASA, in Thinking Machine Corporation, in Intel, everywhere, they're running this code. And it's just beautiful, right? If you look at the cut, it looks beautiful for the finite element, whether it's a 2-dimension and 3-dimension. And when I left NASA to go back to MIT, Horst Simon again said to me, he said, you study geometry and graph theory. I really hope you can prove a theorem on spectral graph theory, on this wide spectral partition work. So this actually eventually lead to me for long, you know, Dan Spielman is a really world expert in spectral graph theory back then, study, you know, the expanders for communication, for many things. So Horst Simon's thing really injected in my mind also, there's something really practical people really love, but clearly in the worst case, it didn't happen, right? It's an NP-hard problem. And then as I began to go to those conferences outside the theory, and I began to be exposed to like conjugate gradient, which is this beautiful algorithm using for solving linear systems. And it's parameterized not by worst case, but by condition number, right? If your condition number is small, conjugate gradient is fast, right? So then when you expose again to the linear programming, then Renderger's result also stated in almost parallel way about this condition number is small. So he's really gave you a sense that you know you have this landscape of complexity, and then somehow in different fields, whether it's practice or in theory, they're able to somehow find some kind of classifier to say that is a condition under which things are efficient, right? So then when we go back to our own theory, I began to deeply appreciate that earlier result by Lipton and Tarjan. So basically said that if you have planar graph, then you can have small separator, and then linear system can be solved fast, right? So you also have this kind of a condition cross the landscape and be able to identify a domain. And then when you go to Intel, this is great result because our circuit all look like planar, right? So somehow match their condition, right? So I feel this type of condition clearly may not just derive from a theoretical study. We try to find the good classifier, but somehow in practice, they might just be there, and these require a theoretical, investigation to see how we can classify them, right? So in something a large domain that if you think about algorithm analysis, it's really like dimensional reduction. right? Because we have this very high dimensional data called the landscape of computing, right? Whenever I give an algorithm, you have this exponential dimensional space data, right? For each instance, you have certain complexity for a particular algorithm. And when you move algorithm around, this landscape also changing. And in some sense, we try to measure them. It's really become a dimensional reduction, right? Because how do we summarize this exponential dimensional space into either a single function, low dimensional function also, or in which way we can find a meaningful subdomain that somehow interpret its efficiency or other qualities. So from this perspective, I feel each generation probably will be exposed more and more to the things that we just never realized before to be an important condition. And this could be one of the reasons to continue to drive our desire for going beyond worst case, right? Because worst case is just one way to do dimensional reduction of your exponential dimensional landscape. And there's many other possible meaningful way. And maybe eventually there will be axiom about what is a good measure. And maybe we can begin to put in certain desirable properties that may cover certain applicational domain. So that's my opening for now.
Hi. So let's see. So I think what I'm going to talk, just say a little about is, so how did I personally get interested in non-worst case analysis, and then maybe sort of then kind of now, what do I think is sort of some of the most exciting things? So in terms of how I personally got interested, when I was in graduate school, I was interested in approximation algorithms. I was particularly looking at graph coloring, and there's a problem where there's this huge gap. So you have a 3 colorable graph, and the best we could do is get n to some power number of colors. Okay, and that's kind of what I was working on, and and it's just a frustrating problem. When you start looking around, I saw that there were plenty of results for the average case, so for random 3 colorable graphs that showed that very simple strategies could find you an exact optimal solution, on average for random 3 colorable graphs. But then when you look at them, one thing I was noticing is that some of them were much more brittle than others. So what do I mean by brittle? So this funny thing that, a random 3 colorable graph looks like a particular. So a random graph looks like a particular graph, right? So you kind of, it sounds funny because it's like most, right, or average, but really, it's kind of like what do most pixel, black and white pixel images look like? If you take a pixel image and you flip each pixel black or white independently, what you're going to get is snow, right? Like on the old TV set. So that, they're all very particular, and some algorithms were very, exactly tied to it, whereas others seemed, more reasonable. And so, what do you mean more reasonable? Like, how do you quantify that? And then it kind of struck me that, well, if you imagine an adversary creating the graph, but their decisions about what edges to put in or not put in were going through a noisy channel, then actually some of these algorithms would still work as long as there was at least some negligible amount of noise in this channel. And whereas others, really relied on the thing being, exactly a random graph. And so, this kind of struck me as something that you could use as a way to go between the random case and the adversarial case. If you think of an adversary constructing something through a noisy channel, and that just like approximation ratio, you could use this as another kind of yardstick. So, approximation ratio is one yardstick. Well, how much randomness, how much noise do you need to add to the adversary's decisions would mean another very reasonable yardstick. And then you could try to, optimize that. So I guess that was kind of, and then at some point I was talking to my dad, because this is how conversations go in our family, and he said, oh, that's that, in cryptography that would be called a semi-random source of randomness. And so okay, so this became the semi-random model. So anyway, so I guess my initial interest is that trying to get other yardsticks, right? As ways to try to make progress on some problems, or maybe you're banging your head against the wall working on a more traditional yardstick. I guess I would say that right now there's just two things I find particularly exciting. One is that the power of deep networks, for example, has really shown that you have these algorithms that are working on things that people want to do, where worst case, they should be, they're all the sort of the way you would code up, what do we mean by the training problem? Those are all NP hard. They should require, exponential amount of time to solve, and they should require huge amount of samples to do it. But nonetheless, by using very natural gradient descent based algorithms, people are able to do instances they want to solve very well, efficiently, and from not very much samples. And so if as theoreticians we want to provide insight, we need to somehow go beyond a traditional worst case view, whatever that means. So that's one thing. The other thing I find exciting is kind of several lines of recent work on using machine learning kind of in algorithm design and kind of in fact, even thinking of algorithm design as a machine learning problem. And I'm thinking here of kind of work, some of this direction spearheaded by Nina Balkan at CMU and some by Piotr here on this panel on kind of connecting machine learning and algorithm design, which I think also has potential to give us a new way to think about what are our goals in designing algorithms. What does it mean to come up with a good solution? Maybe instead of competing with opt, we want to compete with the best algorithm in some family or something like that in a way that these methods can really help us with. So those are the things I'm personally very excited by right now. So with that, thank you.
Hopefully it's working for you. Does this work? No, but
I see. I have to use the mic.
Yes.
Okay, hello, can you hear me? All right, good. All right, so Russell asked us all to share personal experiences with beyond worst case analysis. So let me start by saying that I'm personally a big fan, actually a huge fan of worst case analysis. I have always been. I'm not sure if we're supposed to say it. We're supposed to criticize, but it's a really fundamental framework, and for the longest of reasons. Ravi articulated some of the more intellectual reasons. It stimulates a certain way of thinking and so on. But I think that there are some, I would say, very practical reasons, right, why worst case analysis is important. And the chief reason is that if you have a worst case algorithm, it always works. Okay, you just don't have to worry about if you have an efficient worst case algorithm, right? You can always use it, right? And this is something that like as theoreticians we often take for granted. But it's worth repeating, especially when talking to other fields, like maybe information theory or signal processing, where worst case is not always the main paradigm, right? So for starters, if you have a worst case algorithm, you don't have to worry about adversaries, right? Adversarial effects on the running time, I mean, they don't happen that often, but they do. Sometimes, right? And if you have a worst case algorithm, you just don't have to worry about that. Now, a more typical situation is that the input to your problem might not necessarily be adversarial, but it could be just very messy, right? Because what often happens is that the algorithm is not just like a one-shot module, but it's a part of a bigger system. The system can change. The output of one component becomes input to another. Right, so in principle, it might be possible to characterize the distribution of the input to your algorithm, but it's very hard, right, and it can change over time. So if you don't have to do it, and that's exactly the worst case guarantee that the algorithm provides, then you can just plug and play, and not worry that if you change the system, like somehow your algorithm could stop working. Okay. So these are the big benefits of the worst case analysis. But at the same time, it's important to be realistic, right? So I think about the worst case algorithm as a holy grail, right? So of course, this is something that you can aspire to, right? But it will not always happen, right? So here is a list of things that we could want from our algorithms, right? You probably have your own list, and it's you want to aspire, for your algorithm to satisfy all of this, but I don't know about you, but if I only published papers, with algorithms satisfy all these constraints, my publication list would have been much shorter, right? So, so it's important to be realistic, right? I mean, you have to pick and choose and, kind of live with the trade-offs between these different aspects. And, unfortunately, there are trade-offs between, worst case guarantees and some other aspects, right? So, if you have a worst case algorithm, presumably it's not going to be as simple as it's possible, right? Because, you have to provision for corner cases, right? So this is going to complicate your algorithm, right? And for the same reason, if you have an algorithm which is efficient in worst case, it might end up not being as efficient in practice as you would hope for, right? Precisely because you have to over-provision with respect to cases which just not going to happen that often, okay? So, so it's important, to understand the trade-offs between these things. And, this is something that fascinated me for a long time. I haven't really done much about it, except for in 2013, we had a working group by National Research Council, which addressed many of these topics. And we discussed it a lot. We agreed that it's very important. We had absolutely no idea what to do about it. So instead of proposing solutions, we just decided to do the second best thing, which is leave it as an open problem, right? All right, so so basically that was the status quo, at least from my perspective, until recently. Now, what changed is that over the last few years, there is maybe not a new, but certainly a rejuvenated line of research that goes under several names. I'm referring to it as machine learning for algorithms, but there are many different names for it. The names are not necessarily that important. What's important is the essence. And the essence of this line of research is essentially to use machine learning to improve the performance of classical algorithms, right? And by classical algorithms, I really mean classical problems, right? So things like sorting, searching, and so on, right? They are not things that you would normally think about as being in the domain of machine learning. But this new line of research, makes it actually possible to use ML to solve problems like that. There are various ways of doing it. You can use machine learning as predictors, or you can just optimize over space of algorithms. Like the reason that, at least to me, it's particularly appealing, is that what has been observed is that in many situations, you don't run the algorithm just as a one-shot, right? You keep solving the same problem, day by day or week by week, right? Of course, we are not solving the same problem, right? It's not the same input, because if it was really the same input, you could just don't have to solve it many times, right? So you are switching, from input to input, but those inputs are similar, but not quite different, right? So if you can somehow characterize or extract those commonalities between different inputs, characterize the distribution, and exploit it to make your algorithm more efficient, then you would get a big win, okay? At the same time, what happened over the last decade or so is that machine learning was, around for a while, but especially over the last 10 years, it got really good, right? So it got really good in extracting useful patterns from the data. So now if you combine these two things, right, you have a good pattern extractor. Then if you can somehow use those patterns to improve your algorithms, that potentially offers lots of benefits. And this is something that many people, including myself, have been very interested over the last few years. It's been a very active field. You know, just over the last 1 year, there has been 3 workshops. Actually, 2 of them happened. One is still upcoming at this coming Stock. And, you know, there are already a bunch of success stories. And I should emphasize that those success stories are not only in things that you would associate normally with machine learning, but, you know, these are classic combinatorial problems like data structure, online algorithms, and whatnot. So this is a line of research that I am personally very interested in. The one lesson, you know, that became apparent to me is that respect to this particular line of research, design is as important as analysis, right? And this is because you know, many of these algorithms that use machine learning, I mean, they don't even exist, right? So it's not the case that there are algorithms that work well. We have to analyze them. In many cases, we have to figure out, right, how to use machine learning, you know, to speed up, I know, searching or sorting. Right, so design in this context is at least as important as analysis, but of course, analysis is also very important because you have to understand, you know, how this algorithm work and when they are efficient. So just to summarize, I love worst case. I also love beyond worst case. I think that you know, there are some very interesting opportunities for marrying the two, and you know, I'm very excited about this line of research. Thanks.
Thank you.
So I'm going to ask some questions that kind of like pick up on these themes. So I'm going to skip the warm-up question that I mentioned. But so once we start going beyond worst case, if we're doing worst case analysis, we don't really have to think about what the input looks like. That's just given to us. But if we're trying to go beyond worst case analysis, it seems to me we have to like think about the backstory of the input, how that input was generated, what it means. So when you think about going beyond worst case complexity, what kind of backstory are you thinking about for where that instance came from? And so Ravi, maybe I'll start with you.
Well, I was saying stochastic models, for instance, of data is one place to look to see what's going on. I mean, because we can't do it perfectly, of course. And worst case, I should say, like Piotr, worst case is certainly an important thing to have around for complete guarantees. But I think stochastic or other models of data would be nice to have for problems for which there is a lot of data.
Okay. Santosh?
Yeah, generative models of various types have been very useful. Like we have in compressed sensing or in matrix recovery, whether it's random or stochastic block models and so on. Yeah. But your question is, what do I have and what should I think of the data as?
Yeah.
Maybe so some kind of generative model. What is generating it is an important question. And I guess, for example, these GANs that Kostas talked about are part of this game. Yeah.
So let me pick up on that. So the GANs, you have to like adapt. There is a distribution, but it's also being learned and adapted in the different stages. And so your algorithm has to sort of play against an active player trying to figure out hard instances for it.
Right.
Is that?
Yeah, that sounds.
But then that's going to like converge to worst case, isn't it?
Is it? You tell me. If you play this game, does it mean that because you still they still have to stick to a distribution?
Yeah, in the limit. Okay. So, Shang-Hua, do you think that having like a fixed stochastic model is a good?
I think in general, probably clearly the data come from different reasons, and one is to have the model to generate the data we see. The other one sometimes is the intrinsic properties that the practical problem somehow possess. So, for example, years ago when I was working at Intel, I had a few industry exposure, and working with one of my former office mate from CMU. And at that time, we are trying to write in transistor level simulators for the Pentium. And they want to do this parallel simulation of this large Pentium back then compared with the machine size. And so my friend, Manfred Kara, his name, has this intrinsic belief. He said, this has to be efficiently simulatable on parallel machine because the Intel circuit use so much pipeline that, they are parallel circuits. They are designed for efficiency, and within the efficiency, there's just a lot of native parallelism. Then he said, if the circuit is parallel, there must be a way to enhance this in your simulator to capture it, right? So to a large degree, also, for example, if you look at a lot of either power law or scientific computing, when they are doing like a rocket simulation or airplane the dynamics, and most of the finite element graph, they have certain conditions, right? Because geometrically, they cannot have Taylor expansion go wrong. So the Taylor expansion gave a certain numerical condition. And remarkably, some of those conditions are intrinsic, also related to efficiency or the quality of solutions. Right? So that may not be directly in the generative model, but somehow, because the nature of application has a certain property, and if we are able to somehow harness that property or machine learn that property, then maybe one can somehow adapt to the, right?
So I think this brings up an important point. So many of the instances that we're trying to solve were either created, either are created by nature in some sense, or are created by human effort. And for those two like backstories, the properties, the humans, the people, the systems that people are designing, creating the instances might also give us clues as to the nature of the instances and the best algorithmic approaches to solve them. Is that what you're saying?
Right. So for example, like Avrim's talk about the semi-random, or eventually inspired us to do the smooth analysis to a larger degree. So when you go to talk to the practical people at that time, because I think in late 90s, NSF organized, I think Descartes together with Papa Dimitriou, they organized several NSF conference talking about the future of theory of computing, how can we be closer to practice? And so then when you go to practitioners, they always say practical data are easy. Somehow there's like a folklore there. But when you ask people what is practical data, it is very hard for people to define naturally. And eventually, when Dan and I was talking to folks on how do you model certain practical data, some of our friends suddenly said one thing. If you look at stock market, if you say IBM stock is $170, you believe it. They said if you say IBM stock is 120, you believe it. Or if you say IBM stock is $0, you don't believe it. Or IBM stock is $1 million, right? So somehow he said, when you measure the stock, it's not a number, it's really a model plus something noise, right? So I think those are to a larger degree, like Avrim said, that when you look at certain graph, it's like a graph formed then because certain indecision or certain inability to perfectly design, somehow certain nature come. So that's another property, right? It's almost like, you can say it's a generative model too. Like combine worst case to something, right? But on the other hand, it's kind of generic property that often in the data, right?
So Avram, what's your viewpoint? Do you think that sometimes the data is kind of like the ideal is generated in a way that makes a certain algorithmic approaches ideal?
So let's see. Let me give two answers. Yes and no. Okay. No. Let's see. So I mean, one answer is which maybe is along the lines of these machine learning based algorithms would be something like regret. So or a more fine grained analysis. So like what you would like is an algorithm that if your data, if the typical instances are nice, you do well. And so typical instances are not nice and you don't do so well. And that, you end up doing as well as you could hope to do given how nice the instance, like, so you can, one way to think of this is, you want a really, more fine-grained kind of guarantee. Something
You
like
want
that.
like an optimistic algorithm.
Something like that, right? So if the data is good, you do well. The other thing I would say is that for problems where, yeah, I mean, why are we able, like, why does gradient descent seem to work for training deep networks, right? So there is something about the instances and so forth that, except maybe I would say like this: when we define the problem, we typically define things syntactically in a clean way. SAT is the da da da, TSP problem is da da da. We define it, but in the instances, sure, they belong to that clean problem. But this clean problem, it's clean in a syntactic way, but it's complicated in a hardness way. And maybe there are properties of the actual instances that are allowing these simple algorithms to work, but they are not captured by the way we've defined it. So what are they? How do we get a handle on that? How do we give some theoretical like guidance or insight or something? And I don't know how, but we need, so from that point of view, it's more like going beyond this sort of clean problem statement to something that maybe can give us insight into why these algorithms are doing something.
Yeah. So sometimes when I present like NP completeness to my grad students, I usually say, NP completeness is about the way you formulated the problem. It's not about the instances that have actually come up. And you can always overgeneralize and formulate a problem to be NP complete if you're, but identifying parameters. Okay, so I'm gonna move on to Santosh and say maybe, sorry. Why am my mental, okay. I'm gonna go home soon. Piotr, so you mentioned like the unreasonable success in machine learning in designing algorithms. Is there, is it a function of how we define the problems that we're asking these things to solve? Are we being too rigid in how we define problems, do you think?
That's good. So first of all, like I really like this dichotomy that you mentioned. I think it really matters whether inputs are generated by nature or by humans. Nature tends to be nice, sometimes it's even, as nice as Gaussian. Doesn't always happen, but nature generally doesn't, work against you, right? Humans are much more messy. And, at the moment when you have humans, you have interactions, you have feedback loops, components, and, occasionally adversaries, right? So that's where the, situation becomes much worse, right? So, so the worst case analysis, was designed to handle everything, right? No matter what the input is. The methods that, many of you guys mentioned, whether it's, why SAT suddenly becomes easy or, like other problems become easy, right? This is a phenomenon, and it has something to do with the complexity of the instances. Personally, like we theoreticians really like to have clean models, right? So, I think that this is something that we aim to. But personally, I think that ultimately, we might not be able to explain, why certain, certain problems or certain inputs are easy or hard. But the fact that we cannot quite explain it doesn't mean that we cannot exploit it, right? So that's, like that's where this, idea of trying to characterize the input, input complexity implicitly comes in. Right, so the input might not be Gaussian. It might not be, beyond worst case analysis, according to some clean definitions, right? But the fact that we might not have a simple characterization of it, doesn't mean that we cannot use it. And so maybe this is a kind of a pessimistic perspective on things, but I think that this is something to potentially look at.
Do you? Yeah. Yes, please.
So one thing I guess is whether humans generated it or science generated and so on is not. I think we shouldn't probably worry about it. In other words, it's not our department, right? So I would like our models of data to be simple and nice. For instance, independence between data points. It's not always valid, but Gaussian or uniform or power law, some simple things. So worst case should be replaced by something just as clean, but quote unquote more realistic is what I think would happen. This is controversial, but I don't think we are going to spend time understanding how all data is generated.
Okay. Well, so let me suggest like a different viewpoint. Maybe we should kind of sometimes reverse the quantifiers. So usually we look at an algorithmic problem and then look at the algorithms that solve that problem. But often what happens is that there are actually algorithms that people are using, and maybe it would be good to take an existing algorithm or algorithmic approach and find the problems that or instances that it solves.
Got to be careful about quantifier reversal, right? Instead of there exists an algorithm for all inputs, you don't want to say for all inputs there exists an algorithm.
No, okay. What I mean is treat the algorithm as the object of study. Santosh, you?
Yeah, absolutely. I mean, certainly this is going to be important, right? Whether it's gradient descent, like Avrim mentioned, or learning whale communication, where you have some, you actually have methods to do these maximizing probabilities. Or I was thinking, actually, the two talks that stuck in my mind are, of course, the chips and salad talk and the mermaids talk. And then the chips and salad makes me think of something like the small worlds model, right? Where you're coming up with a model that explains a phenomenon. Mm-hmm. In this case, we want to have a model of data which explains an algorithm success. I think that's a great beyond worst case perspective. Some structure plus randomness often works, but maybe that's not it. You need some insight into what the actual model is. Yeah.
Okay. So one other thing that your talk mentioned, Ravi, is that sometimes, so in worst case analysis, we try to measure the time in terms of the input size. But the input size may actually be a function of the algorithmic approach in many cases. So, or the problem formulation. So then you mentioned like sample complexity. So, the more samples you have, the bigger the input size is and the slower the algorithms are allowed to be. But maybe an n-squared algorithm that actually uses a much smaller value of n is preferable to a linear time algorithm that needs a lot more samples.
So in that sense, pack learning model was a departure from this, right? It said if you have enough data, your answer is going to be correct, however you find it. And then there's another question of how much data do you need to actually run the algorithm. Yeah. So it separated these 2 points.
Yeah. So do you think there are other situations where we could look at algorithms from the point of view of how much data do we need to collect to run the algorithm?
Yeah, indeed, for unsupervised learning, for clustering, actually, the simplest sense of, or mixture learning. How much data is there for you to be able to assert the algorithm I run? I have found the correct mixture or the correct clustering. Mm-hmm. That's an open question, I think.
Yeah. Avram, do you have?
Shafi had a hand up.
Oh, Shafi. Okay, great. Shafi, could you use a mic?
So the question to Piotr, on your slide, you had this one point where you were saying that some problems share. Could you give an example to elaborate? Could you elaborate on that point?
Well, so I wasn't really saying anything deep, right? So, I'm thinking about situations, like you are in a company, every night you have to process the data that came the day before, right? So, presumably the data from day to day are not that different, but they are of course not the same, right? So there is some patterns. There are some patterns in this data. You might not be able to necessarily explicitly characterize it, right? So I agree completely with Ravi that if we can cleanly characterize things, we should do it by all means, right? But I think that in many cases it's just difficult, right? Or we just don't know how to do it, right? So the question is, can we exploit this? There are apparent patterns in the input, which might not be necessarily characterizable explicitly, but implicitly, right? And can we learn such a structure, and can we use the structure to improve algorithms?
So I thought you were talking about the fact that maybe if you have a collection of instances or a
That's
collection of
correct.
problems,
That's correct.
that it might be easier to solve them as a collection
Yes.
rather than individually,
Yes.
because they might give some advice about each other, or there might be a similar structure there that you could discover by having multiple related instances rather than individual ones.
Precisely.
Uh-huh.
Yeah. So So
whether it's by finding a pattern, I guess it's finding some kind of pattern that enables you to find structure to solve it. Yeah.
So that's what I was referring to. So like that, there are various approaches to this problem. I mean, one approach is completely agnostic or empirical. Just train this thing, and try to find patterns and then use it. There has been some theoretical approaches to that. I think you had a paper, and it's definitely something that is still an open problem. But I think it's I think it's a very promising approach to get the algorithms faster.
And I guess my other question was maybe to Costas, was not on the panel. I think you have some work on evolutionary trees, right? About like doing a longest common subsequence when you're assuming that it was sequences were generated by some sort of process. Seems related.
Yeah. So right. So yeah, that's an interesting point on beyond worst case. So sometimes, problems are NP hard if you assume that the data is just arbitrary. But like when you try to learn a model, so you typically when you try to learn a model, you soon separate the source of the data, the sourcing of the data from the problem of trying to do, say, maximum likelihood. So like oftentimes when you separate, like if you don't think about where the data came from, and you think about the problem as an algorithmic problem, hey, here's some data, maximize likelihood, you may find the problem is NP hard. But if you actually say, look, I know my data came from a model of this type. Now, for that kind of data that was sampled from a model that comes from a family, I want to do MLE, then MLE oftentimes is actually not intractable, right? So I think that goes back to what the panel was discussing earlier, where we have to think about the sourcing of the data is important. And that comes up a lot in this kind of trying to learn a model. Okay, I mean, if you're trying to learn a model, it's reasonable to think that the data that you use to learn the model came from a model from some family. And oftentimes that actually sidesteps intractability results. Yeah, and there are several examples of that.
Thank you. We need you to have a microphone again.
I got it. No, I was just saying, you were saying about coming from nature, that we also have some models of nature that come from, let's say, physicists or biologists. We don't have to invent it, and we can maybe use those models. I think it's more like what Chang Tao was saying. There are models that people in the discipline have thought about, that have structure, that have physical principles that guide them, and those could be describing the inputs that for which we need to design algorithms. And I don't think we do that much, but maybe we should.
Yeah.
Another challenge, I think, return to your discussion about the algorithm as a subject, right? Namely, I think data-driven algorithm design, one thing put the spotlight is how do we represent our algorithm, the space of algorithm to solve a problem, right? Because intuitively you want to say there's a nice space of your algorithm to solve this problem, right? And I think some of the success largely rely on that. Somehow you can have a low dimensional parameterization of your family of algorithm to solve the same problem. And therefore, when you see samples, then you begin to be able to fine tune this underlying relatively low dimensional space of algorithm. But for in general, I think it's a great subject that is, you know, we come here, we see so many beautiful algorithm design. You know, this advanced data structure for max flow, you know, the variety of way to do the convex set, right? So those algorithms, if you ask me, how do you yourself parameterize to somehow able to find this algorithm? I don't have a clean language to say what would be the space of an algorithm that solve the max flow, right? So more generally, clearly become much more complex. So I don't know what, but maybe eventually we are able to gain much more insight in have a language for.
Great. So this is, I hate to break up this discussion, but I think we're like way over time today. But I had one last, is Jean Honorario here? So he had a question that he mailed me. So I was wondering if you'd like to ask.
Oh, yes. Well, after the presentations, maybe I'm not sure how relevant it is because in the machine learning community and the information theory community, the generative models, or also known as planted models that people have been using, those have been used a lot. But maybe another angle that that has been also seen is not looking at the algorithms for the exact maximization or minimization or approximate maximization or minimization of the function, but to recover the the hidden true parameter that created that, right? And we have seen that in some of the problems like matrix completion or like linear, the sparse linear regression, and so many other cases as well, like community detection, similar to clustering, etc. So what I wanted to know is like, what's the opinion or any consensus or your opinion about these models, right? Because it's not just about, or it's not much about the approximate optimization of a function, but or guessing the true solution that generated the model. Like, what's the view of the theoretical CS community? It has been used a lot in information theory, signal processing, and so, but what's the view of the theoretical CS community about that?
So I think this raises a bunch of questions. So let me try to repeat them before like giving the panelists time to respond. So one is, should we be looking at algorithms rather than solving problems, but to understand data, understand the distribution that data is coming from? I think we'd all agree that we should, but maybe people want to comment on which approaches. The other thing is planted models in particular, and I think those are, as Santosh mentioned them in his talk, are really good benchmarks for algorithm design. I guess also Avrim mentioned semi-random models as like really good benchmarks where you have like some structure that you've has been placed in it, and then you're trying to see whether you can algorithmically recover or to what extent you can algorithmically recover this structure. Santosh, maybe you want to.
I think Avrim has an answer for this.
I guess, I mean, I would say, I find these sort of problems of yeah, so the problems of trying to recover like a true hidden solution, I think are right. They come up a lot, and I think it's a very interesting question of how, theoretically to model those problems, which you could do through a probability distribution, or you could do through trying to understand, postulate properties that you think are satisfied, and then can you come up, what properties are sufficient to recover the answer or a small structure that contains the answer. Actually, I'm kind of heading towards some work that Santosh and Anita did on this in the context of clustering, where you could have a purely deterministic model, but where you say, here are some properties that of the answer I'm looking for with respect to the data I have. Can I find an algorithm that will, what properties are sufficient to uniquely either identify an answer or to get close? And then sometimes these can lead to interesting beyond worst case type of models. So for example, if you take clustering and formulate as an optimization problem, then you're kind of implicitly saying that the optimal solution to your optimization ought to be, the right answer or something close to it. And if you formulate as an optimization problem that's NP hard and you're only going to approximately solve, you're sort of implicitly saying that approximately optimal solutions ought to be close to the right answer. Okay, so what does that mean, right? So I think that gives you actually, that gives you a potential, formulation that then you can try to work with. So I think these problems are very interesting, and how to, there's different ways to try to formulate them that I think can potentially provide interesting insights into these.
All right. Anybody have any last comments?
Are we going to let people ask questions?
Oh, okay. Yeah, we have one question there.
Can you hear me? Yeah, thanks for the inspiring discussion. So I have a questions about provable analysis. So in some sense, provable analysis actually is like a worst case methodology we use in theoretical CS. But in other like theoretical subfield in like say theoretical physics or theoretical biology, they're not necessarily like shooting for like a perfect mathematical guarantees. So I'm curious about like people's thought here. I mean, I personally also love mathematical proofs, but is there any possible like a methodology, theoretical methodology we can like vision in the future when we want to attack those kind of difficult problems?
Yeah. So let me paraphrase again. So the question is like, to what extent is theory, does theory mean that we have to have provable guarantees for algorithms? Does a theory of algorithms mean provable guarantees? To what extent can a rigorous theory still have algorithms without provable guarantees? And so one thing that comes to mind is I think it's Heldkarp very early on, where they used a LP approximation to evaluate algorithms. So often it was an upper bound on the quality of the solution, and the algorithms often came within 1% of this upper bound. So then that's kind of a instance by instance proof that they're very close to optimal. You think of other situations where we have.
So empirical evidence is a big tool in operations research and machine learning and other areas. There's a debate whether theory should allow or do some empirical validation as well. Seems a good idea in a sense, but we have to be very careful because.
The question was more about
Yeah, okay. All right.
Yeah, that's how I interpreted it also.
Yeah, I think the question, please correct me if I'm wrong, was more about the level of formalism. The level of formalism we usually work in, it's essentially just one step removed from being able to logically list an entire theorem, right? Like step by step. But physicists, for example, often use limiting statements that they sort of believe or are sort of true in principle, but it's very difficult to write down a formal proof. Right, like I'm like cavity replica method,
and
right?
are sometimes wrong.
Yeah.
So,
Yeah.
no, so I mean, I don't think we want to give up the rigor. It's
Okay.
okay to change the problem and relax it, but yeah.
I see the 0 minute sign was waving a few minutes ago. So what I'm going to suggest is that this is a great discussion, and let's thank the panelists and give people who actually want to get on with their day a nice opportunity to leave. And then these chairs are comfortable, so we can continue to sit here and chat for as long as we want after.